Um, so I think it's interesting that there's some problems that when you study them classically, they seem to be quite complicated to solve. And yet when you look at them in the quantum model, a structure arises, and it turns out you could take advantage of it, and the quantum algorithm actually ends up being quite simple. And so this talk is about one class of such problems, the problems of evaluating formulas. Another example might be factoring, though. And so the way I'm going to attack formula evaluation is I'm going to draw a connection between two models of computation, the model of span programs and the model of quantum algorithms. So the main results of this talk will apply to arbitrary Boolean functions, but I thought I'd start by giving the motivating example, which is this formula evaluation problem. And so a formula is just a rooted tree, where the nodes of the tree correspond to gates. So if a gate has k children, then it corresponds to a function from 0, 1 to the k to 0, 1. Now the evaluation of the formula is defined recursively in the natural way. You put the inputs up at the leaves, and you evaluate each gate going towards the root. And that's what you want at the end of the day. You want to evaluate the root. So a special example of this kind of problem is the class of and/or formulas, as shown here. So in an and/or formula, you have a rooted tree, and you can say that gates at, say, an even distance from the root are and gates at an odd distance from the root are, say, or gates. And these formulas are important for various reasons. For example, they correspond to two-player games. The nodes of the tree correspond to histories of the game that the players can play. The leaves are marked 0 or 1 according to who wins in that position, white or black. Then an AND gate says, well, an OR gate says, does white have a winning move? An AND gate says, does white have a winning response to every one of black's moves? And so evaluating that kind of formula corresponds to the kind of question, does white have a winning strategy in chess, say?
So Ben, you didn't say explicitly the words lead once. You mean lead once, not. So this is every variable
Yes.
occurs just once in the formula.
Yes. Yes. So what is known about evaluating these formulas? Unfortunately, not all that much. So deterministically, any deterministic algorithm might have to look at every single input bit to evaluate the formula. If you have a randomized algorithm, though, you can do potentially significantly better. So for randomized algorithms, actually the best lower bound we have is just n to the 0.51, whereas the upper bound, as I said, is n. So there's quite a gap there. But for specific examples, we can do very well. So for example, if you look at the balanced binary and/or formula, so it's a binary tree with the leaves at uniform depth, log base 2 of n, then this can be solved using the standard algorithm is known as alpha beta pruning. You pick a random subtree, evaluate that recursively, and potentially evaluate the other if necessary. And this takes expected time about n to the 0.75. And that's optimal. This is classic work due to Saxon-Wigderson and Santha in the late 80s or early 90s. And actually, they conjectured that tree, the balanced binary and/or formula, is the worst case in terms of the separation between randomized and deterministic complexities. But so far as I know, there hasn't been too much progress on this conjecture since then. And in any case, I'd really kind of like to understand more complicated problems. So, for example, I liked, yeah.
The question, I remember a talk by Farhi a few months ago about results using quantum algorithm to evaluate these formulas. That's faster than 0.75.
Yeah. The classical algorithm is about 0.75. The quantum algorithm we'll get to, it'll be about square root of n. In this case, it will be square root of n.
The classical low bound is, it's 0.51 or 0.49?
No, 0.51. So the complexity algorithm, at least zero error, never does better than square root of the deterministic complexity. And these problems are already basic. The deterministic decision tree complexity for them is always n. So it cannot be square root n. There are formulas for which the non-deterministic complexity is square root n. But for randomized, this node result of mine, the Rafi-Ayman, is 0.51. So you beat a little bit. You get a low bound And randomized complexity, that's a little better than non-deterministic complexity. Right. In fact, it works even in the case that you have threshold gains, not just answer now with this lower bound.
Yeah, there's a bound there too.
It's a more general case, so it's
We didn't frequently.
Well, so we'd like to understand formulas over larger gate sets. So here is a problem that's been studied before. It's a recursive three-majority function, a balanced recursive three-majority function. And so for this problem, the best lower bound we know is 7/3 to the depth. That's from 2003. The best upper bound, well, we don't know it though. We don't know what the correct algorithm is. But it is known, this was shown all the way back in the original Saxon-Wigderson paper, that the optimal algorithm is not like the alpha-beta pruning algorithm. It's not directional, it's a technical term. It sort of does not have a recursive structure following the structure of the formula. And so it seems to be kind of a complicated question to solve classically, even though it's simple to state. And one obvious question here is why do we care about majority? And this goes back to an obvious question. Of course, you can expand any formula out in terms of and OR gates, but when you do so, that will require duplicating some of the inputs. And when you start duplicating the inputs, you create dependencies, and that's not what I'm interested in. I'm really interested in the problem where all the inputs are independent of each other, so the problem is very cleanly, recursively defined. And these are called read-once formulas. And so one of the corollaries of the work I'm going to talk about is actually going to be an optimal quantum algorithm or an almost optimal quantum algorithm for all these kinds of problems. So we'll be able to deal with majority gates, AND gates, OR gates, parity gates, whatever. In fact, an arbitrary finite gate set. And maybe, I've never looked at it carefully, maybe an arbitrary gate set over logarithmically many bits. And actually no balancing condition is required. It doesn't have to look like this. You can have different gates at different positions. It can be a very skewed tree. If you do have a assertive balance condition, then it actually becomes an optimal quantum algorithm. So instead of almost optimal, losing a log factor, with a balance condition, you can shave off that log factor. And also what's sort of interesting about the quantum algorithm is that it turns out that it will have a recursive structure that tracks the recursive structure of the formula. So unlike what we saw classically, alpha-beta pruning does not work in this case. The quantum algorithm will look very much like the structure. It won't be classical recursion, it'll be some sort of quantum recursion, but it works out. And in any case, I think it's quite nice that this problem that seems to be classically sort of intractable to solve optimally, quantumly it has a very nice solution. All right, so here's my one slide summary of quantum information processing. So I hope this is a review. I'm not really going to go into it. But I just wanted to sort of remind people of the basic difference. The basic difference is that classically, if you have n bits, your state is a 2 to the n dimensional vector of probabilities. Quantumly, your state is a 2 to the n dimensional vector whose L2 norm is 1 instead of the L1 norm 1. Classically, you can apply stochastic maps. Quantumly, you can apply rotations. Classically, at the end of the day, you sample from the distribution to get your answer. Quantumly, you can also sample. But let's specialize to the model I'm mostly going to be concerned with today, which is a model that's known as decision tree complexity or query complexity. So here you're trying to evaluate a function, and I only care about the number of bits of the input you have to look at to evaluate it. So say consider this tree here. The black labels tell you what bit to look at. So here I say, look at bit x1. If it's a 0, go up. If it's a 1, go down. Say it's a 0. You look at bit x2. If it's a 1, you go down to look at bit x3. If it's a 0, you go here and you output 0. So this is a decision tree. It computes the majority function. Another way of picturing it is just as a circuit where time is going from left to right. These are arbitrary operations independent of the input x. interspersed with queries. So a query takes an index j and it returns xj. And the decision tree complexity is the number of queries you have to make in order to evaluate the function, which is equivalent to the depth of this tree. So quantumly, the tree doesn't exactly generalize, but the second picture does. So we can define quantum query complexity in essentially the same way. So it'll be the number of queries you need to evaluate the function. We're going to be talking about with bounded two-sided error. Classically, a query takes an index j, returns xj. Quantumly, any operation has to be reversible. And so it's going to take j and a bit b and return j, xj, xor b. And also, it's going to be a coherent query. So if you run it on a superposition of inputs, you'll get the corresponding superposition of outputs. That's why I put it in a ket here. And so the query complexity quantumly is the number of queries you have to make. For example, for the OR function, which corresponds to searching for 1 in a binary string, the deterministic decision tree complexity is n, randomized is theta of n, and the quantum case is actually just square root of n. And that's Grover's algorithm, yeah. And it should be said that that query complexity isn't really what we care about when we're designing quantum algorithms. Yeah?
When you said the query is can be in superposition, so the j is fixed, or the j can also be in...
The j can also be in superposition, yeah.
So how does a complicated query, single query look like?
It'll look like sum over jb of psi jb, which is some state, tensor jb, and the result will be the same sum, the same psi jb, except j xj plus b.
Is it clear, or you want a more detailed answer? You
Is
can
it?
write it on the board just as
Yeah.
superposition query, so that
Yeah.
in case people are probably will not matter much.
b
JB is times some kind of
Yeah.
coefficient, right?
Yeah, this is a coefficient, but it could also be a state,
Yeah.
more generally.
But it's a tensor, so it won't change.
And it maps to the same sum, j xj plus b.
You basically ask all the questions in parallel with the appropriate way.
And in between queries, you can make an arbitrary unitary transformation.
That's right. That's right.
And that's not charged.
That's not charged for us. So that's right. So this is not really what we care about when we talk about quantum algorithms. We really care about how hard it is to implement those arbitrary transformations.
I also ask, what does it mean in this case that you have two lines and query only sits on one, on the picture? I mean,
Oh, I see. Yeah, that's confusing. So the first line is just to represent the workspace of the algorithm. So the psi jb in this case. That's passed from one level, from one time step to the next.
What you remember about your previous state is kept in this other line, and is input only to these unitary transformations, not to the query.
So the space is a direct sum of two subspaces.
A tensor product of two
Tensor
subspaces.
product,
Hmm?
A tensor product.
Tensor product.
Yeah. Yeah. Okay. And
One of the multiples just carries the data with it. I mean,
yeah, that's what I'm trying to
So the
indicate
number
with
of
that
things.
slash. Yeah. So what we really care about is not the query complexity. We care about the time complexity, which is how hard it is to implement these other operations here between queries. And it's certainly the case that the time complexity can be much larger than the query complexity. It can take many local gates to implement every one of these arbitrary gates.
Well,
Yeah.
You count the number of input bits you look at. You count all the different j's in all the superpositions?
No. Every one is a query. Every superposition is one query. That's the power of one.
Yeah, so this is maybe a confusing way of saying it. Really, I'm just counting the number of queries, but each query can be a large superposition.
You can think of randomized query. I mean, it's an analog
I suppose.
Like
Yeah.
you are.
Yeah.
The question in certain probabilities.
Maybe since we're discussing,
If
so
it was a
so what is
stochastic matrix, it would be exactly randomized reflexes.
what is the exact condition of this whole composition?
So the condition.
Representing something as a composition of these elementary steps, but
Yeah.
so what is the condition of the total?
So when you these are just unitaries independent of x. When you multiply them all out, you'll get a big unitary that does depend on x. And you'll look at the first bit, you measure it, and you say that's your answer.
So you start with the all zero state and you measure the end of the first bit, you'll get f of x.
Hopefully, I'm allowing for bounded error.
With good, we say 2/3.
Yeah, say. Of course, you can study the exact problem too, but it's less interesting, I guess, in this case. Okay.
So you start with one particular state and then project to one linear
At the end of the day,
function at the end.
yeah. And so it certainly can be the case that time complexity can be much larger than the query complexity, even exponentially larger. For example, the hidden subgroup problem, it's known that the query complexity is small, polylogarithmic in the size of the group, but nobody knows how to solve it efficiently. It could well be that the time complexity is exponentially more. So why do we care about query complexity? There's a few reasons. One is that most quantum algorithms we know of actually are based on good query algorithms. For example, factoring can be seen as being based on a query algorithm for solving the period finding problem or order finding problem. A second reason is that it's actually a practical model that it can be implemented if you can implement quantum computers. So, for example, if the input is given by a function, and you have an efficient classical circuit for computing that function that takes j to xj, then you can put that into your quantum circuit and everything stays efficient. A third reason, which is sort of a classical corollary of all these results, is that if you have a good quantum query algorithm, an algorithm with low query complexity, that actually gives you a low degree approximating polynomial to the function of interest. And so these kinds of polynomials are interesting even outside of quantum computing.
And not just approximate, also exact.
Uh,
Approximate and exact are very closely related in an infinity, right? So,
What, in the bounded error case?
yeah.
I don't understand.
Well,
If
for total functions,
For total functions, yes.
but mostly,
But
well,
it's
yeah, here this is,
always a total function.
yeah, but here
Ah.
Nissan Segedi.
yeah, but here the exponent matters though.
Yeah, so maybe you care about it. But anyway, the degree, if you change it up to a polynomial, then approximating and computing exactly a function are the same.
Yeah, that's right, for total functions. And maybe a last reason is just for caring about this is just that, that we can do things with it. Like we can prove lower bounds about it, which is a practical reason for caring. And so actually we have two main methods for lower bounding the quantum query complexity Q. The first one is this polynomial method. It just says if you can prove let's see, if you can prove that the approximate degree of a polynomial has to be at least a certain size, then that proves that the quantum query complexity has to be at least that same amount, actually at least half that amount. You lose a factor of 2.
Then what is the degree?
The degree.
So what type of approximation?
Sorry.
What type of approximation exactly?
L infinity.
Okay.
You want to get it correctly for every input with distance, let's say 1/3. So if it's 0, it will be between plus or minus 1/3, and if it's 1, it will be between
For every
for every input.
Okay. Yeah. Okay. So that's the first of the methods we have for lower bounding quantum query complexity. The second one is what's known as the adversary method, which roughly says how much we can learn from the system with a single query. I can go into more detail if you like, but this is the answer. This is what the bound is. So it's a semi-definite program. It says maximize overall matrices, gamma, that are entry-wise non-negative. I'll say what adversary matrix means in a second. Of the operator norm of gamma divided by the maximum operator norm of gamma j. All right, so gamma here is a matrix that's, if it's an n-bit function, total function say, it's a 2 to the n by 2 to the n matrix. So its rows and columns are indexed by the inputs to the function. An adversary matrix means that it's non-zero only in those positions where the function is different. So if you have x and y and f of x is equal to f of y, then the adversary matrix is 0. If f of x is not equal to f of y, then it can be anything, although in this case it has to be non-negative. And then gamma j is a matrix that contains only those entries x and y, where xj differs from yj. So that's like the difference in querying the jth bit. And so here, the norm of gamma can be thought of as the amount of information we have to learn. The maximum gamma j is the amount of information we can learn, the maximum amount of information we can learn by querying a single bit. The ratio tells you a lower bound on the quantum query complexity. This is called the adversary bound. And actually, so these two methods are unfortunately incomparable. Here are some examples that show this. Say the element distinctness problem, the approximate degree is n to the 2/3. The adversary bound, it's known as just square root of n. It's at most square root of n. I don't know if it's known to be square root of n. Another kind of problem is what's known as the Imbinus formula. Here, the approximate degree, in fact, the exact degree, is at most 2 to the d, where d is going to be the depth of the formula and n is 4 to the d. In this case, the adversary bound is 2.5 to the d, so it's better. So we have these two methods, and unfortunately, neither one of them is good enough for all problems. Yeah?
In gamma j, is there still the condition that f of x should not be equal to f of y when there is a...
So gamma j is exactly the same as gamma. So in particular, it has that same condition.
Okay.
Except it has some entries zeroed out. Yeah, it's a submatrix.
So the Harchenko method for formula lower bound.
Seems somewhat reminiscent of communication complexity.
It is like in formula because
So in 2007, the situation with these two bounds was somewhat changed. So Hoye, Lee, and Spalek came up with a new adversary bound that they call adv plus minus. I started calling it the general adversary bound, and Peter didn't mind. I don't know about Troy. So you can call it the negative weight adversary bound or the general adversary bound. I prefer that. Either way. So it's exactly the same, actually. It's exactly the same SDP, except you see it doesn't have the condition that the matrix be entry-wise non-negative. So the entries can be positive or negative. And it's still a lower bound on the quantum query complexity. And so what's known about this? Well, it can be better than the adversary bound. So for the Imbinus formula, it's 2.51 to the d instead of 2.5. It's not known what it is for the element distinctness problem. And the funny thing is, we don't know what so we don't know what that, but we also don't know what the query complexity of the Imbinus formula is. So now we have these three methods. This is obviously strictly better than that, or at least as good as that one. So it's still two methods, but they still seem to be incomparable. And so this is a bit of a puzzle that I'd like to solve. The second puzzle we're going to solve in this talk is the problem of evaluating formulas. So this started back in 2007 with really a breakthrough result by Farhi, Goldstone, and Gutman. And they showed that when you have this balanced binary and/or formula shown at the right, this can be evaluated with a little bit more than square root of n queries. And this was generalized in two directions. First of all, we generalized it in Binus, Childs, Spalak, and Zhang to consider loosening the balance condition. So if we loosened it only slightly to make it approximately balanced, then we were able to get a square root of n query algorithm. For an arbitrary algorithm, we were able to get back to square root of n times a little bit more. But maybe a more interesting generalization was to the problem, we kept the balance condition, but we can try to extend the gate set. And so this was Robert and I. And we showed that if you have a balance formula over a gate set that includes all 3-bit gates and a few more, then you get an optimal quantum algorithm for evaluating these kinds of formulas. And I want to explain where this comes from a little bit. But here's a special case of the theorem from that paper. So let f be an arbitrary Boolean function, and define fk to be the same function concatenated on itself to a depth of k. So fk is a function on n to the k bits. Then we said if you have what's called a span program that computes this function f, then you get a good quantum algorithm. So the query complexity of the quantum algorithm is going to be at most what's called the witness size of the span program raised to the kth power. I'll describe the witness size in a second, but basically if you have a good span program, you get a fast quantum algorithm for evaluating these kinds of formulas. And the real statement is of course more general, but this is a simple way of stating it.
How is f evaluated exactly? F to the k?
You feed.
Commit as a sub.
It's n, right? It's n. It's degree n 3.
It's degree n 3.
Yeah, that's right. That's right.
So the quantum complexity of decay is that just like the quantum query complexity is always O of the witness size, and that just the witness size has this property that you can take the k out, or what's?
That's a good question. And that's part of what we're going to try to address. So far, this is all we knew. And so here, for example, even though I say f is from 0, 1 to the n to 0, 1, f is a fixed function, and n is not an asymptotic parameter. K here is what's going on in the big O.
So should we think of n as a constant?
Yeah.
Because
In this theorem, not in all the previous slides. You probably should have been better.
I should have put k and n.
Yeah.
Yeah. Sorry.
so this means that the witness size is always an integer, or it can be fractional.
It can certainly be. Yeah. It doesn't have to be an integer.
Because like the exponent will depend on the precise witness size. That's what you are saying here. Like if it's
But it's an upper bound.
it's equal. No? Oh, it's an upper bound.
It's an upper bound. Anyway, we'll generalize it. So
It's an upper bound, but for many examples, it's not an integer, and there's a matching lower bound, so it actually is tight. Yeah.
This witness size is between what and what, and for f, between 1 and n, or
1 and n, yeah, 0 and n.
so it's a constant also.
Mm-hmm. Mm-hmm.
And I forgot the answer. I missed the answer. It's an integer or not an integer?
No,
Not an
in
integer.
general not. Yeah. Okay, so I'd like to define span programs and define the witness size. Let me do that quickly so this makes sense. A span program is actually pretty simple. It has two parts. First of all, you have some vector space. For me, all the vector spaces are going to be over the complex numbers, because that's what makes sense for quantum computers. It's not what people studied before, for the most part. But you have a vector space, you have a target vector, t, in that space. And then you have two n input subspaces, v0, v10, v11, v20, v21, and so on, vn0, vn1. And that's what a span program is, a vector and a bunch of subspaces. We say that it computes a function, f sub p. F sub p evaluates to 1 exactly when the target vector lies in the span of the subspaces that are available to you. So the span of the subspace is vj, xj. So if x1 is equal to 1, you're allowed to use v11, but not v10. And you're allowed to use all these vectors and take a linear combination of them, and your goal is to reach the target. If you can, you say the function evaluates to 1. So here's an example. So it's a two-dimensional space. The target vector is pointing off to the right. v11 is this subspace, v21, v31. I'm just ignoring the negative ones. You could say they're all 0, or they're just not there. And this span program computes the majority function, majority out of 3. Because if you have just one of these subspaces available, you definitely cannot reach the target. But if you have 2 of them, well, then you can span the whole two-dimensional space. So in particular, you can reach the target. And the same idea will work for general threshold functions. Just to work in a k-dimensional space, throw in n random directions, you're going to get threshold k out of n.
So this leaves the possibility that it's both 0 and the t.
No.
So
Either
it's-
you can span it or you
it's
cannot span it.
Uh-huh.
It's a function.
So it's a one-sided. It's kind of an asymmetric.
It seems like it's an asymmetric function definition, and it also seems like it's a very odd definition because it really depends on like the precision. If the target vector lies very close to this span, it still says 0, right? If it's not exactly in this span. And so we'll have to take care of that in the complexity measure. We want that to be a bad case in the complexity measure.
These vectors have to be real. So these are whether
Complex, but real is okay too.
So, for example, well, I guess you still didn't talk about measures of complexity.
Not yet. Okay.
So you can compute any function in this?
Can I?
It's complete. You can compute any function.
Yeah, it's easy to see actually. Well, yeah, we'll see it a little later, I guess.
And what is the resource again? It's the dimension of the.
So classically, what people cared about is what's called the size, which is the sum of the dimensions of all the subspaces. Quantumly, I'll define it in a minute.
The sum of the dimensions is an analog of formula size. This model can simulate formulas, and what will take the role of the size of the formula will be the sum of the dimensions, or the number of occurrences of variables.
So I thought I'd give a brief, very quick summary of how how that formula evaluation algorithm worked, which will sort of give you a preview of how the more general algorithm is going to work. Basically, what we do is we take a span program like this one. We write it out as a matrix. So the target vector in this case is 1, 0. So I write it like that. The first column is 1, 1. That's this, which I've chosen a basis for it. Then 0, 1, and minus 1, 1. So that's this matrix. We then consider that as the biadjacency matrix for a bipartite graph. So there's 2 vertices here that corresponds to these 2 rows. 3 vertices here correspond to these 3 columns. And the weights correspond to these entries. Yeah, so this edge here is the 1, 0 edge. And then for a given input x, I'm going to add edges above the vertices here that are not available. So for example, if the input is 1, 1, 0, I add an edge above this guy because it's false. You can't use this entry. When you do that, it's simple to see that the span program evaluates to true exactly when this graph here has an eigenvalue 0 eigenvector that's supported on this vertex here, meaning it has a non-zero coefficient on this vertex here. So let me show that. Here we are. So we can assume that the coefficient is 1 by scaling if it's non-zero. And then to be eigenvalue 0, we want everything to cancel out at the internal vertices. So at this vertex, we want the sum of its neighbors to add up to minus 1, or to 0, but the sum of these neighbors should add up to minus 1. And does it? Oh, yes, it does. Sorry, because this edge is weight 0, actually. So the weighted sum does add up to, I think I have a sign error. This should be minus 1, maybe. And then at this vertex, again, the sum of its neighbors should add up to 0, 1, -1, that's good. And you see what this vertex does is it forces this entry to be 0 because we can't use this vertex. And so that's what's going to enforce the span program.
This is just an implementation of the linear combination that gives you the target vector.
That's what it'll be. Yeah, that's right. And so really, eigenvalues, 0 eigenvectors of this graph, of course, basically evaluate the span program. That's how it works. But that doesn't tell us a couple questions. Like one is, how can we actually find these span programs? So I said if you have a span program with small witness size, which again I'll get to, but if you can find that, then you'll get a good quantum algorithm. But where do these span programs come from? And they can be quite complicated. So this is the sort of thing we were doing. We were playing around in Mathematica, and you come up with a function. This is probably like, I don't know, maybe exact 2 or 3 out of 4, but I'm not quite sure. You write down some function. It has, here I've left some free parameters. You run this Mathematica function. It optimizes the parameters, tells you the witness size. And sometimes it's good. Usually it's not, so you have to try again or something. It's quite hard. I guess what can I say? I'm not good at coming up with span programs. And so that's a question.
I guess one thing that you demonstrate there is that the generalized adversary bound is not tight, or what's that mean in like this?
Yeah, so the second question I'd like to talk about is what the connection between the span program is and the adversary bounds. So here I have a table, and the rows of the table correspond to different functions, 4-bit functions. And I've listed for each one the adversary bound and the general adversary bound. So this is always better, or this is always at least as good. Sometimes it's strictly better, sometimes it's equal, or I've just put a dash. And this column here tells us what the best span program we were able to find. So that's an upper bound. And we put a check mark. This is just out of the paper. We put a check mark if we have an optimal span program that matches the adversary bound.
So you didn't explain. You explained why you get an eigenvalue for a graph problem, but you didn't explain how to implement it with a quantum query algorithm yet.
That'll come later. I'll give you a more general algorithm. Yeah.
And your examples seem to be tailored to the case where or maybe it's easily generated, where 0 is not an empty subspace, but rather.
Yeah, so the example I gave before, that majority, it was what's called a monotone span program. It only used like the V11, V21 subspaces, but in general, you can have non-monotone span programs as well. You can use positive and negative literals. So one yeah.
What is the measure associated with the span program that you're shown on?
It's a witness size, which I think is maybe 2 or 3 slides away. But I just wanted to say a little bit about where we're coming from still.
So what is this matrix? Is this the same matrix as in the previous slide?
It's the same kind of matrix, just for a different span program.
So this you write for a fixed function, right?
Yeah, so it computes some fixed function. We had some crazy notation where we allowed multiple literals to be associated to the same subspace in some cases. That simplifies the calculations for Mathematica.
So
it's not necessary.
The number of columns is up to you, or?
Yeah.
It's really the size of the product, the number of columns.
Huh?
At least in our original definition for size of span program, that's the size.
And
It's the sum of the dimensions. If
And you delete everything that's not. You can use only columns that are true or something.
Yeah. And this is supposed to be the target vector, I think. I'm not sure.
Is it obvious what the columns should correspond to? Like that they should correspond to some kind of like subsets of variables or subsets of literals, or is it obvious that these
This
are
is
the
the
columns?
definition. That's the definition. Every, right, in this span program, every column corresponds to, it's a vector in one of your subspaces. So it's associated to some literal, to some variable in its value. You can use it only if that variable has this value.
Could you, I'm sorry, could you go back to the first slide where you define the span program again?
Yeah.
So this VI's, so this did not talk about what the dimensions of the space was. Right, so you just said that there is some abstract space somewhere, and you have these subspaces.
I guess you can show maybe that it doesn't need, you don't need more than the sum of dimensions for that.
Well, you just put the basis for each one of these subspaces in a column, right? You take a basis for each subspace and you put it in, you know, all these basis elements in a column, and that will give you the matrix that you showed in the later slide.
Yeah.
Wait, now I'm also stopped. So
Yeah.
the matrix consists of numbers or of vectors?
The columns of the matrix are the vectors, and the vectors span these spaces.
So for each bit, we have two subspaces, right?
That's right.
One corresponding to it being 1 and one corresponding to it being 0.
Right.
So each of these subspaces may have arbitrary dimension.
So there may be many columns associated to the same literal, to the same bit. Yeah.
So to the same bit, you may have many columns associated to it being 0, and then many columns associated to it being 1.
That's right.
As much as the dimension of it.
When you say literal means a bit together with its value?
Yes, yes.
Okay.
Yeah.
See, one thing we noticed when we were putting together this table is that in the cases where the two bounds are equal, we almost always have a check mark. So we almost always have a matching upper bound. Not always. In this case, we don't. But in the cases where there's a gap between the two adversary bounds, like here for the ambinus function, it's 2.5 versus 2.51, and the best upper bound was much worse. In fact, for no case where there's a gap were we able to find a matching span program. And so my conjecture in this time was that maybe there's some connection going on between the adversary bounds and the span program witness size, and that only in those cases where the adversary bounds were equal would we be able to find a matching algorithm. And that in the cases where there's a gap, we would always have a gap. That was my conjecture. But a third question is, of course, can we use span programs for more than just evaluating formulas? Formulas are fun, but maybe we can do more things with this technique as well. And so we're going to answer both of the first two questions fully, and the second question partially. And so these two theorems give you the idea. First of all, we show that for any Boolean function, the best witness size of any span program computing that function is exactly equal to the general adversary bound. This is achieved. So in fact, my conjecture was just wrong. The reason we weren't able to find an optimal span program here was just because we're not good at finding span programs. It's not because they don't exist. And the second theorem is going to be a quantum algorithm for evaluating span programs. So I'm going to show that the quantum query complexity is almost equal to the witness size up to a slightly sublogarithmic factor. And so this says that indeed span programs are useful for developing other quantum algorithms, not just formulas. So if you find a good span program for an asymptotically large function, you still get a good quantum algorithm for evaluating that function. Yeah?
Can you reformulate theorem 1 just using approximation by low-degree polynomials? This is equivalent to the...
Let's see if I do that.
Adversary was the difference thing. It was not
So
Yeah, this is about the adversary bound.
this is not related to the degree of...
Well, so the second thing, you can say the second theorem is actually an upper bound on the degree of the approximating polynomial.
But together these two things show that the adversary, generalized adversary thing is tight, right?
Yeah.
That's right, I hope. Yes. Yes. So that's the point. As a corollary of these two theorems, we have the lower bound that the query complexity is at least the adversary bound, and now we get a almost matching upper bound for every Boolean function. And so in particular, it lets us fill in this table. For the Imbinus formula, we now know the query complexity is 2.513 to the d. For the element distinctness problem, because the adversary bound is tight, is nearly tight, it must be at least n to the 2/3 over log n, because we had a lower bound of n to the 2/3, and actually there's a matching upper bound. I have no idea what the adversary matrix is in this case, but I know it has to be at least, has to give you a bound of at least n to the 2/3 over log n. Another corollary of this kind of result is that it gives us a simpler SDP for quantum query complexity. So an SDP had been known, and it had sort of the form that you'd expect. So if you're looking for a T-query quantum algorithm, you wrote down an SDP with maybe T or T+1 terms, and you had inequalities relating each of the terms to each other. That's kind of what you'd expect. It's a little bit more complicated than that, but that's essentially how it worked. And here it's
Terms or T full matrices?
well, it'd be T matrices. Yeah. Yes.
Now that you know this, did you try to use the approximate degree explicitly to lower bound this number? So you know that the adversary degree is at least the adversary plus minus is at least the approximate degree up to some
Log, yeah.
log. So now there are these methods to bound certain things from below using the approximate degree.
That's what they did.
Try to do it explicitly. So
Yeah, that's
you take the
I-
so this duality thing. So you see,
But this actually upper bounds the degree, because you know that the degree is always a lower bound on the quantum query complexity, whereas this kind of agrees with the quantum query complexity.
yes.
So this upper bounds the degree.
No, so for element distinctness, they show that the adversary, the only way you know to lower bound the adversary plus minus is using the degree, right?
yeah. I don't know how to do it directly or even indirectly. I don't know how to translate this result into an adversary matrix.
What do you mean? You can also lower bound it with the normal adversary bound.
Yes, but you only get square root of n. Oh, that should be square root of n.
For the element distinctness.
Yeah. And so we have this one SDP due to Barnum, Sachs, and Zegedev. But now we also get another SDP, which is just this adversary method, and it's much simpler, right? It just has this one matrix gamma, so it's still exponentially large. It's a 2 to the n by 2 to the n matrix, but it's polynomially smaller, so that's nice. And also, it's sort of it's not the obvious form. It's not the form with T+1 terms relating one to the next. It seems I use the adjective greedier because it just says, this is the amount of information we want to learn. This is the amount of information we can learn with a single query. Take the ratio. That's not exactly it's not exactly greedy. It's
I would say it's an
But-
absolutely remarkable formula or fact that the adversary, quantum adversary bound is just captured by within logarithmic factor by this bound. I mean that's absolutely remarkable.
Yeah. Another kind of correlate you can draw from these two theorems is that span programs are really the same as quantum computers, quantum query algorithms. So if you measure your quantum algorithm by query complexity and you measure your span program by witness size, they're almost the same up to log factors. So that's sort of interesting as well. That I mean, span programs have been around since '93. Quantum query algorithms, I don't know when they're first formalized, but late '80s, early '90s, almost the same time, and they're actually equivalent with the right complexity measure.
So for a fixed Boolean function, you can write a span program of any field, right?
Yeah.
So is it always, I mean, can it be harder over one? Is the width size field dependent? When you have big gaps, or
So the witness size,
What is the witness size? I don't know.
which I will define. Sorry, it's more slides than I thought. Right now, the witness size is only defined over C. The size, the sum of the dimensions is defined over any field, but the witness size,
So it's only defined over.
yeah, yeah, yeah.
Size, you take the span program, you forget about it, you look at the optimal query algorithm for the
So does this get a result for general Boolean formulas that wasn't done before?
Yes, so this will turn into another of the corollaries will be optimal or near optimal quantum algorithms for all sorts of formula evaluation problems that wasn't known before. And the reason for that is going to be that, well, actually, I mean, you could say that this gives you an optimal quantum algorithm for every problem, right? You just compute the adversary bound, and that gives you the algorithm. It's not so easy because the adversary semi-definite program is exponentially large, so you can't generally compute it. For a formula, it turns out that you can compute it separately for every one of the gates and then plug them together. And so if you give me a formula, I can efficiently compute the adversary bound, and I can efficiently come up with an algorithm.
What was known about the witness?
If it's read once, it will be optimal. In general, yeah.
What was known about the witness size of span program for general program formulas? For
Well, I mean, this is just something we defined, so.
Maybe we should let them define it, and then we can discuss it.
And yeah, so let me define that. Skip over those slides. So once more, here's the definition of span programs. Here's a similar example to what I gave before. This one computes the and function. And it's a very simple definition. There's no qubits and scillas, unitaries. But it's a little bit funny because there's lots of span programs that compute the same function. Here's another span program that also computes the and function. You need both of these
How should we
subspaces.
look at this? 2 dimensional or 3
2 dimensions.
Okay, good. So these 2 vectors span the plane.
2 dimensions, you need both of these vectors to reach the target vector. So it computes the and.
can you flash the previous slide? Yeah, what about the previous slide?
This is a review of the definition of span programs. So you have a target vector and a bunch of subspaces. Okay.
So now you have witness size not just p but also the particular input.
Sorry. So the witness size is going to depend on this angle. I want this span program to have a smaller witness size than this one, because intuitively this is crazy. I mean, those subspaces could be extremely close to each other, and so you're going to need a really long linear combination of these vectors to reach the target. Whereas this one, it seems to be much more efficient. And that's the intuition I want to capture in the definition.
So it's like the norm of the combination.
Yeah, it'll be the squared norm. Let's put it down. So if I want to make sense of this, I need to choose a basis, right? It doesn't make sense to say it's a long linear combination here because I don't have a basis. And so the first thing I do is I put a basis on the span program, or so each of these subspaces, I put a set of vectors that span that space. And here again, I'm putting them as the columns of a matrix, okay? And then we have this algebraic criterion. So the function evaluates to 1 exactly when the target is in the range of those columns of this matrix that you're allowed to use. So pi is a projection onto those columns. And the witness size is going to be the shortest linear combination of columns that reaches the target. It's the least squared length of any linear combination of columns that reaches the target, which can be written just like this. We want a times pi, that projection, times w to equal the target, and then we want the squared length of w.
So why is it between 1 and n?
Yeah, why is it between 1 and n? Oh, it's not actually. It could be more than n. It could be, in this case, it could be arbitrarily large, and actually it could be arbitrarily small as well. It could be less than 1.
If it's equivalent to the query complexity, then
I'm not done. This is only the definition for f of x equal to 1, and I've defined it for a particular x. The witness size of the span program will be a certain maximum. So the maximum will have this equivalence. And so I've defined it in the positive case. I want to define some analog in the negative case when the function evaluates to 0. And so when the function evaluates to 0, it means we have this subspace here. This is the subspace that we can achieve, that we can reach. and the target vector lies outside that subspace. And so that means we can find another vector, which I'm calling W prime, which has a non-zero inner product with the target, but it's orthogonal to the range. So we just rotate the target so it becomes orthogonal to this subspace here. And let's say it has inner product 1 with the target. Okay. So now the existence of such a witness is equivalent to the function evaluating to 0, to the span program evaluating to 0. And the witness size will be the squared length of that, the least squared length of that witness, where you weight that witness by the adjoint of the matrix I had before. So we want that witness to be short, weighted by the columns of that matrix.
The adjoint of the projection of the matrix?
Well, it doesn't matter, because so the condition that the vector be orthogonal to the range is this condition here, WA pi is equal to 0. So if I put this matrix, this term here is only supported on 1 minus pi. So I could put a 1 minus pi there if I wanted, but it doesn't matter. And I think the intuition here is sort of that if the target is really close to this subspace, then to get inner product 1, you're going to have to make the witness be really long, and so that's going to be very expensive. That's sort of my intuition.
So under this definition, it's clear that witness size is closed under complement, taking the complement of the function.
Yeah, actually, so one thing to realize, the definition was not symmetric, but you can have a dual for a span program that, just reverse it. So it is, span programs are symmetric, without changing the style.
And
It
the
follows just
duality.
this duality of linear programming, of linear equality equation.
So the same duality will just translate witness size of 0 to witness size of 1, so you'll get.
Yeah, that's true. Is that obvious? To some people.
The duality of linear equations, so
That's
if
true,
there's
though.
no solution, then there is another vector that's orthogonal to your target.
So that gives us the witness size for a given span program and a given input. The witness size of a span program is just the worst case overall inputs of those witness sizes. And this thing, well, again, it could be, it's at least 1, but it could be arbitrarily large. Let me give you an example. So let's try to get OR. So I'm going to work over the one-dimensional space. The target vector is just going to be n to the 1/4. We'll see the scaling, why that's scaling in a second. The vectors are going to be, I'm only going to use the positive subspaces, so I've put zeros in all the negative subspaces. And in the positive subspaces, just 1s. Okay? So this computes the OR, because if you have any positive subspace, you can certainly reach the target. The witness size, let's do the positive case. Say the input is 1 followed by a bunch of zeros. Well, in this case, you need to put a square root of n here, an n to the 1/4 here on this column to get to n to the 1/4. And then the squared length of that is square root of n. So the witness size is square root of n. In the false case, so OR is false on the all zeros input. So we're looking for a W prime that has inner product 1 with the target. So it has to be 1 over n to the 1/4. Then we multiply that by the adjoint of this matrix and take the squared length. And so that should be square root of n as well. And so that's why I chose the normalization of the target, is because I wanted these two to be the same, so that the witness size of the span program is equal to square root of n. I mean, obviously, you see, if you scale down the target, it makes the witness size smaller in the true case, but larger in the false case. And so you can balance them out by choosing the correct scale. And that's what I've done here.
Sorry, what is the witness size in the false case?
It's the squared length of the matrix times this witness W prime that has inner product 1 with the target and is orthogonal to the range. So in this case, on the all zeros input, you can't reach anything. And so that subspace is just 0. The target we have here, we want inner product 1 with that, so it'll be 1 over n to the 1/4. And I multiply it by this matrix, and you're going to get, and take the squared length, you're going to get square root of n. Yeah.
Multiplied by this matrix.
So n times
So it's n times, so it's n to the 3/4. So
e squared 1 over n.
1 over n to the 1/4 squared is 1 over square root of n, and then times n, because there's n of them.
So a vector with n entries, each of which is 1 over into that.
Ah, okay.
Yeah. And so here, the fact that it's square root of n and the fact that the quantum query complexity of the OR function is square root of n, that's not a coincidence. We'll see. But let me say a couple more things about why this definition. Where does it come from? First of all, as has been pointed out already, you can complement a span program, take its dual, to compute the negated function. And that leaves this definition invariant, at least if you use the right dual. There's different ways of doing it. The second reason why this is a nice definition is that you can compose span programs very easily. And this is really the key for evaluating formulas. If you have a span program P and if you have a span program Q, then you can, then you can compose those span programs, and the composed span program computes the composed functions. The witness size will just be multiplicative in that case. Of course, a silly reason for why this is right is that it leads to quantum algorithms. Yeah.
So you have both upper and lower bound here. So I mean, obviously you can compose and maybe get a witness size at most W size, but you say that is actually also at least.
Yeah.
No, that's not what I'm saying. Sorry. Yeah. This should be less than or equal to.
Okay.
Yeah. You can compose them and get something that's at most.
But it should be very close again by.
I don't.
Only for the optimal span
I think it could be less.
Take the optimal span program first.
For an optimal span program, it will certainly be equality.
It will be.
For
It's clear that you cannot do better on P composed on Q than doing it.
let's see. Well, the reason will turn out to be because the lower bound, the adversary bound, also composes supermultiplicatively, and this shows us that the upper bound composes submultiplicatively. So if they're both if they're both equal, it's optimal. Then everything's equality. All right, so let's now go into the proofs of these two main theorems. In the first one, I'll just prove the interesting direction, which says that we can come up with a span program that works at least as well as the adversary bound. And here's an example of the kind of span program we'll be looking at. It's for the AND function. And say we have a target vector with n columns, so it's n-dimensional space. And you think of each of these rows as corresponding to an input. So think of the first one as corresponding to the input 0, 1, 1, 1, 1, 1, and so on. So these correspond to the maximal false inputs. They have 1, 0, and n-1 ones. And then the subspace is just going to be 1, 0, and then this is the identity matrix. And the point here, why does this compute the end? Well, it's clear in the true case. If you have all these available, you can certainly reach the target. You just have a uniform combination of them. But say your input string is 0 followed by a number of 1s. There's no way you can reach the target because you're only allowed to use these subspaces, and they all have zeros in that first row. And so you're trying to reach a 1, but all you have is a bunch of zeros to work with. There's no way. And so that's the idea. Well, that's one simple way to see that this computes the AND function. And I'm going to generalize that idea next. So now I'll consider an arbitrary Boolean function. And I'm going to have a target vector that has all 1s, and the rows are going to correspond to the preimage of 0 for this function. So there's a row for every false input.
Maybe it's worthwhile pointing that the target vector is really can be chosen arbitrarily. That there's a linear transformation that can allow you to pick whatever target vector you want.
Well, yes. I mean, you can rotate all things around, choose your basis however you like. In this case, it's nice to have this basis is rather nice.
But this is no loss of generality for it.
Well, it's no loss of generality because I'm trying to come up with a span program. So I'm constructing a span program that's better than the adversary bound.
But you're not losing generality in trying to construct one by choosing this target vector.
So it's not the length somehow matters?
Yeah, the length may be, but the direction is free.
So now
Well, the whole target vector is free. I'm just trying to come up
That's
with
right.
something.
No, I was just
Yeah.
pointing it out. Maybe it's not
Yeah.
obvious. That
Okay.
So now we're trying to construct a span that's as good as the adversary method, and
Hmm.
and this is a F and the rows. So the rows here are what, like 0, 1 vectors that are n-dimensional 0, 1 vectors that correspond to F.
No. The rows they're indexed by the false inputs to X, to F.
so you are going to show it, right?
Exponentially many.
There's exponentially many rows.
Exponentially
Yeah.
many rows.
Yeah.
That's what we said. So you might need those dimensions, right? So it's not that, like we can assume that these are the only dimensions. You might need extra dimensions.
Maybe you can assume, but it's cleaner to work this
So
way.
you
I
can,
mean,
sorry?
maybe you can assume that there are no more rows than columns, but it's cleaner to think sometimes of many rows.
Well, you can certainly assume that there are no more rows than columns. The columns is the size, and you can change basis so that you're working in effectively a lower dimensional subspace. But again, it doesn't. In this case, it doesn't matter.
This way somehow we decided the dimension of the representation. And I just don't understand how the dimension of the representation can be chosen freely.
Well-
Not that, no. Well,
You said that this could be the target vector,
I
right?
just said that if you have a span program, any span program that works with a particular target vector, you can just rotate the whole space and choose another favorite target vector. That's why it's a trivial observation.
Yeah, but the dimension of the space remains the same.
Everything remains the same. The
No,
sizes,
I
yeah.
think Mario is more concerned about the question
So-
whether it's without loss of generality, always that the number of columns, you can always reduce the number of columns to be, the number of rows to be no more than the number of columns.
Yes, that's also
Right,
true.
but then you could evaluate any formula in polynomial time.
No, I actually was just asking that why can't it be that the number of rows should be more than the number of
Logarithmic
negative
problem.
inputs?
It's a waste.
No, the number of rows can't. Sorry, the number of columns or number of rows.
Well, so the number of rows. So
Yeah.
the number of rows. Well, why? Okay, so what?
Well, first of all, it doesn't matter. The number of rows and the number of columns, neither of those matter because they didn't show up in the witness size complexity measure. Secondly, the number of columns here could be exponential because I haven't said anything about the dimension of these spaces. But if the number of columns is small, it could be smaller than this exponential. That's one possibility. And then everything here is effectively working in a low-dimensional subspace. And again, the witness size definition is invariant under change of bases, so we might as well move everything into that low-dimensional subspace. So you could assume that the space is at most the size of the span program, at most the number of columns.
Yeah, but you agree that there is a lower bound on the number of rows, right? For instance, I can't get away with just one row. So.
Yeah.
So I don't quite understand why we can.
Well, in
just-
the O function, you did get away with one.
Yeah, but for
In
other
general.
functions, in general, you cannot get away with just one.
Yeah, but anyway, it's not a measure that it cares about.
Okay. So I want to construct this span program in the same way that we looked at for the example of the AND function. So for any given row, say x, I want the available inputs in that row to be all zeros. And so this is called the canonical form of this span program. And the point is, like on this input, it has to evaluate to false because you're only allowed to use columns that in this row have zeros and you're trying to reach a 1. And so in imposing this canonical form on the span program forces that when the function evaluates to 0, the span program has to evaluate to 0. We still need to come up with the other condition that when the function evaluates to 1, the span program evaluates to 1. But we've solved half our problem just by choosing the form properly. And the witness size in this case, well, we're looking for something that is inner product 1 with the target and it's orthogonal to the available columns, so we might as well choose the witness to be just the singleton vector that has a 1 in this entry, and then the witness size will be the squared length of all these vectors. The sum of the squared length of the vectors that you look at along that row. That's what happens when you multiply by the adjoint of the matrix. Oh, and I wrote that down. But now consider an input that evaluates to true. So we want the span program to evaluate to true. And so here I've named these vectors vx1 through vxn, these rows in the xth row. And what we want is we want some vector that we can multiply by this matrix and reach the target. So we'll break that witness w into n parts, vy1 through vyn, which are the parts that you multiply by the corresponding subspaces here, either v10 or v11 and so on.
Linear combination that generates a target.
When you concatenate these vectors, it's a linear combination that generates the target. And the condition, let's write out the condition. Multiplying this matrix by that vector should reach the target. That's just this. For every x, it should be the case that the inner product over the sum over j, where xj differs from yj, of that inner product should equal 1. So this condition that it's sum over j where xj is not equal to yj, that's because in the false case we have vectors in the opposite position, like x of 1 is 1, so we have a vector in the 0 column. Here we have vectors in the positive cases. So if y1 is 0, we're going to have a vy1 here. And so you only multiply them when they differ. Can you see that?
No, I'm sorry. So you take the linear combination that gives you the target vector, in the case it's a 1, yes, and you just break them according to the variables, variable
That's right.
names, and they are multiplied by. So
The condition is
what
that
vxj is for all the 2n blocks, or just for the n blocks, which are just the notation. What is vxj?
Vxj is just the xth row of this matrix. Vx1
Non-zero
to
part.
vxn.
vx1 is like every row has like 0 and non-zero, like vx.
Yeah, it's half zeros, half non-zeros.
And it's a true, right? And take that part of the row.
In the false case? In the true case?
So x is an element. It's an index for a row. It's an element such that f of x is 0,
Yeah.
and vx1 is either the first.
It's either this or
first
this.
part or the second part, depending on whether x1 is 0 or 1.
And similarly, that's when x evaluates to false. If you have a y that evaluates to true, vyj will be the opposite, though. It'll be that component of the witness, but in the opposite manner.
So this condition written there is more or less somewhat analogous to the fact that in every, let's say, monotone function, the min term and the max term must intersect. Right? This is what makes sure that the program never computes as 1 and a 0 in a particular instance.
So Vyj is just
Is
a
it?
vector of coefficients for the allowed
Anyway,
columns.
that's how.
So,
So go ahead.
Vyj is just a vector of coefficients you take for the allowed columns, right?
For those columns, yeah, that's right. Yeah.
So why is the witness size not the sum of norms of the vyj's?
Well, here I'm maximizing over both x that evaluates to false and that evaluates to true. So
it's x and y.
yeah. So in the true case, the witness size is the squared length of this witness, which is the sum of the vyj's. In the false case, it's you put a 0 followed by 1, and you take the adjoint, and that gives you almost the same thing. Actually, that just says that the witness size is at most this number. One can verify that it's actually going to be exactly this number if you do things right.
So you could forget about span programs and maybe define things just in this term, right? So
Yeah.
you have these vectors vxi for every I, and I guess
It's equivalent.
yes, it's equivalent. It just might be,
Why is it vector? It's a special span program, right?
but he says that this is actually cannot be without loss of generality.
Yes, but actually, it's true both for the size and for the witness size that you can convert an arbitrary span program into this form, into this canonical form, and it doesn't change the size, and it also doesn't change the witness size. Well, it can decrease the witness size. It can't increase it. I'm not going to prove that. It's true though. All right. So we have this criterion that we're aiming for to come up with a span program. That's here. That's an SDP. Here I've written it in terms of positive semi-definite matrices. This matrix X, whose entries are the inner products between the VXJs. And now it's actually just one step. You take the dual of this SDP, you're going to end up with the adversary bound. You can either believe me or you can look at this slide. I recommend believing me. So I just take the dual, I introduce variables for all the equalities and inequalities. I change the variables twice, here and here. And this term here, it's simple to see, is actually, it looks like this. So the matrix, these alphas form the matrix gamma. And the condition is that the matrix is unsupported on terms where f of x is not equal to f of y, so it's an adversary matrix. And the last inequality is going to be that the identity minus the gamma j's, these sum matrices, is positive semi-definite. And the reason I put some detail here is I wanted to point out why it's important that the functions are Boolean. So if you look at this condition here, it says something about this kind of matrix. So gamma is an adversary matrix. Here, let's see. So I've arranged the inputs, the columns, and also the rows of this matrix. It's a square matrix. I've arranged the inputs as the preimages of 0, followed by the preimages of 1, followed by the preimages of 2, say. Say it's a ternary. Say we have three values. Then an adversary matrix can only be supported on these shaded areas. It has to be supported on rows and columns that differ from 0 to 1 or 0 to 2, for example. And so that's the SDP we're getting when we just push things through. That's not the same as the adversary bound in general. But in the Boolean case, when you just have two of these, this condition is the same as the condition that the matrix have norm at most 1. And that's really the key step where I'm using the fact that the function is Boolean. Then, of course, this is exactly the definition of the adversary bound.
What was gamma j?
Gamma j, so these rows and columns are indexed by the inputs x and y. And gamma j, it's a submatrix of this matrix gamma that only includes terms where the xj differs from yj. They're different in the jth bit. Okay. And so actually that's.
So are you saying explicitly that any adversary matrix defines such a span program?
Yeah. Sorry.
If I just have this matrix
What am I saying?
satisfying this condition, so I can then build a span program out of this matrix.
No, I mean, you take the dual of this SDP. If a solution to the dual does correspond to a canonical span program. That's true. Right? I mean, you take a solution to this SDP, you take the Cholesky decomposition, you get these vectors, you put these vectors in this matrix in this way, by putting zeros in some positions and the vectors in other positions in some careful way. And that gives you a span program for evaluating that function, and the witness size of the span program will equal the objective value of this SDP.
So one way or another, for every gamma, you build a span program. You can build a span program.
For every dual solution, I build a span program. Gamma is a solution to the primal SDP. I kind of skipped that, right from here to here.
So the other question is,
It didn't get to the output.
Oh, you mean this, the equality?
I mean, if you say that it's a canonical form, you didn't lose anything, right?
We didn't answer the
Yeah, maybe let me answer this. So the fact that equality one can say that it's actually trivial because it's a consequence of the quantum algorithm, because we know that the quantum algorithm can't be better, the quantum Poincare complexity can't be better than the adversary bound. And so if this were strictly less, that would give a contradiction. Right? Asymptotically, you would get a contradiction when you compose this function on itself many times. That's kind of a very indirect argument. You can give a very direct argument as well.
Just because of that, no? I mean, if the canonical form is without loss of generality, then everything else was equalities there, right?
Well, there was an inequality in the last.
Well, let's see. Like this statement here is not true. It's actually the witness size is at most this number. So that's an inequality. See, because what I did in the false case, I chose a witness that was all zeros except a 1 in that entry. But there could be a better witness that actually has shorter witness size. Okay, so that proves the first theorem. The second theorem, that from a span program we get a quantum algorithm, goes as follows. It starts with what I started saying before, that we have a correspondence between span programs and graphs. And we're going to use these graphs to compute the function. So we're going to show that eigenvalues, zero eigenvectors of these graphs correspond to witnesses. Secondly, we'll show that, in fact, properties of eigenvalues, zero eigenvectors of these graphs imply that you actually have a spectral gap around zero. And this is kind of the main technical step. And then third is that you can use, once you have a spectral gap, you can use that to find quantum algorithms in sort of straightforward ways.
These are the graphs will be weighted, but the weights will be positive and negative on the edges of this graph. Right?
Yeah, well, they can be complex too.
Yeah, or complex, right?
Yeah.
But so when you say around zero, you look at the Laplacian of this graph, and this will be the lowest eigenvalue possible or not?
No, I mean, I'm just looking at the adjacency matrix of the graph, and so it's a bipartite graph, so the spectrum is symmetrical around zero, and I'm caring about that gap there.
Okay.
And one thing that may be worth pointing out here about the second step right now is that all the algorithms I talked about before for like evaluating and/or formulas, or my paper with Robert on evaluating more general kinds of formulas, they all showed that you actually have a real spectral gap, not just effective, whatever that means. But this statement here, when we prove it, it will simplify those proofs dramatically. So if you look in those papers, there's like 15 pages of proof trying to show that you have a spectral gap in this case. And this kind of statement is going to eliminate the need for those proofs. And so, for example, it lets you prove the and/or result, the square root of n result for and/or formulas in just a couple lines. It becomes quite straightforward. So let me step through these steps here. So once more, I'll define two graphs, G0 and G1. So G0 is the graph whose bi-adjacency matrix is just that matrix A for the span program. And G1 is the same, except it has one additional column, so one additional vertex, which I'm drawing over here for convenience. And it's connected to these vertices, the rows, with weights given by the target vector t. Now to compute a function, I need to make these graphs depend on the input string in some way. And so this is what I'm going to do. Well, here's what it is in terms of that projector, but it's simpler. So I add a vertex for every column. So these again are the columns. I add a paired vertex for every one. And then I add a weight 1 edge exactly when that column is not available. So if this is in v1 0 and x1 is equal to 1, then I add an edge there. If x1 is equal to 0, I don't. And so that defines the graphs G0 of x and G1 of x. And the observation, which we started to make before, is that you have eigenvalue 0 eigenvectors exactly when the function evaluates to 1 for G1 and exactly when the function evaluates to 0 for G0. So here's an example just for the OR function, which I showed before. So we had a one-dimensional space. A was just a single row of 1s, so that's this bipartite graph. And then we had the target vector with a weight square root of n I think it was n to the 1/4. Okay. And here to find the two graphs, g1 of x and g0 of x for two inputs. Say in this case, we're looking for an eigenvector that has support on this vertex. So +1 on this vertex, that can be canceled out if we put a minus square root of n on this vertex and zeros on everything else. And so that's an eigenvalue 0 eigenvector supported on this vertex. And so it works. In this case, the function should evaluate to false. And indeed, if I put say a +1 here, I want the sum of these guys has to add up to minus square root of n. But because of these vertices, I can't put amplitude on any of these vertices. Right? If I try to put something here, that'll contradict this constraint. And so that's the point of adding these edges in this funny way. It forces you, adding an edge here forces this coefficient to be 0. And that was in the true case for g1 of x. Here I've drawn g0 of x for the same graphs. If you put a +1 here, you can cancel it out with a -1 on each of these vertices. If you put a +1 here, well, it's not going to work because you have that constraint. And so in g0 of x, it's exactly the opposite. You get an eigenvalue 0 eigenvector when the span program evaluates to false. And that was just for OR. In general, the proof is completely straightforward. Here it is in the positive case. We're looking for an eigenvalue 0 eigenvector, so I write down what that means. Something equals 0. And I wanted to have support on the first column on that output vertex. And so writing out the two equations, the first one is that the target is equal to that linear combination of the columns of the span program. And the second one says that the vector can only be supported on the available columns, which is exactly what we want for a span program to evaluate to true. And so actually, though, we get a stronger statement than just this lemma, because if you look at the squared, if you normalize the eigenvector, so say normalize it so that the overlap on this vertex is 1, then the squared norm of that eigenvector is going to be 1 plus the witness size. Right? The witness size was the squared length of this portion, and so when we normalize the eigenvector, we get 1 plus that. And similarly, in the false case, the squared norm of the eigenvector will be, for a canonical span program, it will also be 1 plus the witness size. And so we want these eigenvectors to have large overlap on the target vertex, which corresponds to small witness size. Here's the correspondence. We take the matrix A, we put it down into this bipartite graph. Witnesses correspond to eigenvectors, and witness size correspond to the norms after normalization. Okay, so we understand the eigenvalue 0 analysis. That's not going to give us a quantum algorithm yet. For one thing, we have these two different graphs, so we just want to work with one graph and run a quantum algorithm on that one graph. So we need to understand how we can turn the eigenvalue 0 analysis into a spectral gap.
What do you mean run a quantum algorithm on the graph? You will run a quantum walk?
A quantum walk on the graph, yeah. So let's find that. Let's see if we can show a spectral gap. And it's sort of straightforward. You just look at this graph and look at that graph, and you think of this one as a perturbation of that one. And then given that you have a good eigenvalue 0 eigenvector for this graph, you show that you get a spectral gap for this one. And what you actually do is you look at, what I actually do is I looked at the biadjacency matrix here, squared, or take it times its adjoint. And that gives you something like this, where I've written it out in coordinates. I'm assuming that the target vector is just a 1 followed by a bunch of zeros, which you can do by changing coordinates. And then I've diagonalized everything orthogonal to that. And so that's one matrix. The other matrix, this one here, when you square this matrix, it just becomes an additive perturbation in this 1 term. And so it's sort of, and then the condition we started with, that you have a large overlap in the normalized eigenvector, becomes this condition in terms of these coordinates. It's sort of not a completely straightforward problem, but it's not completely hard to calculus problem to show that you get a spectral gap when you have this kind of condition, just by looking. I proved it just by looking at doing everything in coordinates.
How did you get zeros off the diagonal there? That's obvious that you get.
Let's see. I mean, this is a positive semi-definite matrix, and so I looked at the portion that's along the direction of t. That's its first coordinate. And then this matrix here is the proportion that's orthogonal to t. That's also a positive semi-definite matrix, so I diagonalized it.
Oh, you diagonalized.
Yeah. And so all these AJs are non-negative, well, positive actually. And so I'm not going to go through that, but this is the kind of theorem that we can show. And this is what I mean by saying that there's an effective spectral gap. So we started with an eigenvalue 0 eigenvector that has overlap at least delta, squared overlap at least delta after normalization. In the zero case. And what we end up with is, this is what I mean by spectral gap. So lambda is a set of eigenvectors for the perturbed matrix for the one case. And what I show is that the sum of the squares of the overlaps of those eigenvectors on the output vertex is small. So say we have delta is 1 over the witness size, or 1 over the witness size squared, I guess. Then choose lambda to be the witness, also 1 over the witness size. And this will be a small constant. And this will be the squared support of all eigenvectors between minus 1 over the witness size and plus 1 over the witness size. So that's what I mean when I say I have an effective spectral gap. You won't have a spectral gap for sure. You can have eigenvectors very close to 0, but those eigenvectors will have very small squared support on your output vertex, which will mean that they won't be detected by the algorithm.
So what is the content, the algebraic content of this theorem? So you just take a matrix of the form we had, so it's just a diagonal matrix with positive entries, and we add a row and a column, right? That's which has a 0. Yeah, so we have the matrix on the left. This has some 0 value eigenvector.
Yeah.
And now we perturb it a little bit by
here.
But we perturb it here, and we just study the projection of the 0 value eigenvectors of the perturbed matrix, and look at its projection on the first coordinate. I don't know. So it's a lower bound on t in terms of delta.
Yeah. No, I mean, what's happening here is this is some arbitrary matrix. It's almost arbitrary, except we know something about the eigenvalue 0 eigenvector. Here, I want to show that we have a spectral gap. I don't care about the eigenvalue 0 eigenvectors. Actually, it's actually clear that this guy can't have an eigenvalue 0 eigenvector supported on this first column because I've added a positive number.
Well, that's exactly your proof. You're saying that like you have this canonical 0 eigenvector, which when you perturb it, it's moved to something which has which is an eigenvector with eigenvalue a little bit of 0. And like this is the main projection on this one. So if you sum all the eigenvalues which are around 0, which will exclude this one, you cannot gain anything from this projection. That's essentially right.
I don't know if that's obvious.
Okay, you have to quantify this, which like essentially how you graph.
Okay, yeah. Yeah, I don't know. I mean, I don't know if this kind of statement is known or not. It's not hard to prove though. And so once we have that kind of statement though, then we can get a quantum algorithm. And here's how it's going to work. First of all, let me try to give you some intuition. So we have this graph. We know in the positive case it has an eigenvector with support at least 1 over the witness size. In the false case, it has a spectral gap of at least 1 over the witness size, an effective spectral gap. That's not very good because we're not going to be able to detect this eigenvector in the positive case. The support is 1 over the witness size. That's still pretty small. And so what I do is I first scale that target vector down by a factor of square root of the witness size. So if you scale it down, that pushes up the support of the eigenvector on that vertex. Right? So you scale these edge weights down, that pushes up the support here. And then you can make that a constant. Okay. That'll hurt you in the false case, so you'll lose a squared factor in the eigenvalue 0 eigenvector. In the spectral gap, you'll lose the square root, so you'll have a spectral gap of 1 over the witness size. Now we can start to give some intuition. So if you're a physicist, this might be the intuition you use. This first idea is you start your algorithm at this vertex and you measure the adjacency matrix, thinking of it as the Hamiltonian that gives you the energy for your system. And if you measure it to precision 1 over the witness size, then you can distinguish these two cases. Right? If you, in the positive case, you measure it, you're going to get 0 with constant probability, at least 1/2 probability. In the negative case, you're not going to get 0 because you have a spectral gap and you're measuring to a precision smaller than the spectral gap. And so that's an intuition if you're a physicist. I prefer this kind of intuition, which is slightly different. So in the positive case, we have an eigenvalue 0 eigenvector that has large support on the vertex we're starting at. So let's consider the quantum walk. So the quantum walk is the unitary that's e to the I times the adjacency matrix. And so an eigenvalue 0 eigenvector becomes an eigenvalue 1 eigenvector of the quantum walk. An eigenvalue 0 eigenvector of the adjacency matrix becomes an eigenvalue 1 eigenvector of the walk. And so in the positive case, it's a stationary eigenvector. It has a large overlap with the stationary eigenvector. So when we run it, when we run this walk, nothing is going to happen, roughly. In the negative case, we have a spectral gap of 1 over the witness size. And so when you exponentiate that, you'll have a spectral gap of 1 over the witness size as well. If you run it for time witness size, that'll spread out, and it will be far from stationary. You'll be able to tell that something's happened. Here's sort of what we do. One problem when you exponentiate a matrix is that even though I had a spectral gap here, when you exponentiate it, things can wrap around many times. And so it could be that the exponential has no spectral gap, even though we had a spectral gap in the spectrum of the adjacency matrix. And the solution for that is just to choose a random time. So we choose a time uniformly at random from 0 to the witness size. That ensures that, yes, some eigenvector up here could wrap around the circle and end up here, but that'll happen with small probability. Yeah. Okay. And so that's the idea for the algorithm. We want to.
This is standard, just computing an eigenvalue via a random walk with a quantum query algorithm. This is something that was used.
Some of it is standard, but this portion here is sort of not quite standard. It's recent.
So what was done?
So what was done before was stuff by Mario. He showed one way of converting so I call this a continuous time quantum walk, and he showed one way of converting a continuous time walk into a discrete time walk, which is what we really want. But the problem there is that it depends on things like the norm of the matrix.
So wait, what was it for? What do you run the quantum walk for? I give you a graph, and what are you looking for?
Well, so you're looking for the eigenvectors with certain range of eigenvalues supported on a certain vertex. This is how everything works.
So every step in the walk calls you a query. That's like if it was discrete, that's.
If it's discrete, it's just like a classical random walk. You walk to your neighbors, except quantumly, you keep the coin as part of your system, and you don't re-randomize it every time step.
Yeah, but it's one query.
Every step is one query.
In that case, it would be, because like here you can do a walk from here without making any queries, but when you're here, you have to make one query to see if there's an edge or not. So it's one query per step. Yeah.
So I think he's right in the sense that, so we have this amplitude, what is, when you measure the eigenvalues of an operator, right? What is it called? The
Phase estimation, spectral estimation.
So can't you just interpret this as a phase estimation process?
Yeah. That's.
And then the phase estimation is actually standard.
It's a totally standard
And
technique.
so
why-
phase estimation for given graph
phase estimation on a quantum walk on a given graph is totally standard.
Okay.
I think it's fair to say.
What is done?
Well, there's a problem in converting so we want a quantum walk whose spectrum corresponds to the spectrum of this graph here. And there's two ways of doing it. One is by just exponentiating it. And the problem with this is it gives you a continuous time quantum walk, and we want a discrete time walk. We want to make discrete queries, that is. The other observation you can make is you can use Mario's correspondence between these kinds of matrices and discrete time walks. The problem with that is that you lose a factor that corresponds to roughly corresponds to the norm of this matrix. And I have no control over the norm of this matrix because this just came from the solution to that SCP. It could be huge. And so that's why I'm doing things this way via the continuous time walk. All right, so this is what we're trying to implement, e to the I t times the adjacency matrix. But I want to say how can we do this in terms of query complexity? And the first thing we can do is we can notice that the matrix breaks up into two parts, the adjacency matrix. So it breaks up into this left part that doesn't depend on the input at all, and it breaks up into this right part that does depend on the input. And so we can implement the first part very easily. The second part just takes one query, but of course they don't commute with each other. So e to the sum is not equal to the product of the exponentials. And so one standard approach to doing this kind of expansion is just a Lee-Trotter expansion. So the exponential of the sum is equal to the limit as m goes to infinity of these kinds of exponentials. And the error term can be bounded like so. And so if you want the error to be a constant, the number of steps you have to make is about the norm of the matrix times t squared in this case. This can be improved to just t to the 1 plus epsilon using higher order expansions for arbitrarily small epsilon.
What's the hypothesis? Why does the error term not include hx?
Here?
Yeah.
Oh, that's because hx has, these are all weight 1, so the norm of hx is just 1, so I've not written it down.
So that's the hypothesis.
In general,
It's
yeah.
not identity for all.
Yes. And in general, it will depend on like the commutator between the two terms. But again, this is no good because we have a term that depends on the norm of the matrix anyway, and that'll kill us because I have no idea what that is. And so there's a better approach. Let me introduce another model, which is it turns out to be the same. So here everything is acting in continuous time. Instead of making discrete queries to the oracle, we allow an oracle Hamiltonian. That is the sum over from j from 1 to n of xj, j, ket broad jj. And so that's this red portion. It's constant. Then we allow an arbitrary, what's called a driving Hamiltonian. That can be completely arbitrary in time and in strength. It could have impulses that are infinitely strong. And this is a continuous query model for quantum algorithms. And so the complexity measure is how long do you have to run the algorithm. And it's clear that if you have a t query algorithm, you get a continuous time algorithm that takes time t, or maybe 2 pi t, because you just run this. You run the oracle for time pi, and then you apply the impulse for the impulsive Hamiltonian that implements this unitary. Then you run for another time pi to implement this query, and then you apply another impulse to get the next unitary. But the really nice result, which is absolutely key for us here, is due to Cleve, Gottesman, Mosca, Soma, and Young-Mallow just from stock this year. And they showed, in fact, that you can go from the other direction. So if you have a time t continuous query algorithm, you can convert it into a discrete query algorithm that just takes time. You lose this log factor. And so that's really what we need. And the intuition, I don't know, rough intuition is you can think of it as an asymmetric Lee-Trotter expansion. So they deal with the case where one of the terms is much larger than the other term. That doesn't happen in this first expansion, which is what kills you.
uniform superposition?
No.
No. So where is J? Where is this J vector coming from?
This is just a Hamiltonian.
So how should we think of the weights of the queries in different stages?
Do you mean for the conversion or in this model?
In the final algorithm.
Okay. Well, so the final algorithm will be this
I'm
conversion.
trying to, let's say, recreate Grover's search from this.
Yeah.
Right. I mean, that's a very special case. We can see how it should, converge. I mean, of course, there it's not uniform. I mean, you hone on the.
But it's a quantum walk, right? So it's kind of next query is maybe then you can directly see the discrete walk.
Grover search isn't so hard because you can directly see the discrete walk on that graph. And you can show that the norm is actually small, and so it's okay.
Yeah, I don't see it. But
For in the continuous case, I don't know that I can say anything useful. It's just you make some queries. You're trying to simulate this kind of system.
Time t in the continuous case, it's supposed to be some time unit for it. Like time t in a continuous case doesn't make any sense, right? Number of steps in discrete.
No, it makes sense. You define h bar to be 1.
I mean, you are right. It's normalized. So this somehow has to be normalized. This h.
Well, I mean,
With respect to the size of the Hamiltonian or something.
So, for instance, I think this sum of hg squares should be 1 or something like that. So it says hx is normalized.
So this oracle Hamiltonian provides the time scale.
Yeah.
okay.
So you have to normalize it, right? I mean,
Well, certainly, if you allow this Hamiltonian to be stronger, twice as strong, then you can run it in half as
Yeah.
much time.
yeah.
Yeah. So we care about the constant there. Yeah. And so that's really that's it. That's the algorithm. We run the continuous time for the witness size time, and then we convert it to a discrete time algorithm where we lose this log factor. And so actually, if you care about the continuous time query model, which historically people haven't cared about too much, but maybe it's of more interest now, it shows that span programs are exactly equivalent up to constant factors to these kinds of continuous time query complexity. It's only in converting to discrete time that you lose this factor.
But is it necessary that you lose that factor?
It's not clear.
So it is because there is like a factor between the continuous and the discrete, or so you are saying that the span program is exactly the continuous time, right?
Yeah. Oh. Let's see, because you have to wonder what is the adversary lower bound on the continuous time case, and I don't know.
We talked about this, right? Like,
Yeah.
I think it's also a lower bound on the continuous time, but
You just lose a constant or what?
yeah, you use the
Okay.
constant like 2 pi, but I don't know. But they also use a more sophisticated continuous time model or something, right?
That's right. They use actually slightly different continuous time models, so you got to switch models.
Right.
Yeah.
So I thought about it once for the other model, and it was just a factor of 2 pi or something, but I don't know about that.
Okay. Yeah. I mean, one problem, which is why people haven't studied the continuous time model too much, is that there's lots of different Oracle Hamiltonians. There's not one standard that you should use clearly. So here's the model. In general, we solve this STP. We take the Cholesky decomposition. We put them down in this matrix. Here's the formula. We think of this as a bi-adjacency matrix for a graph. We run a quantum walk on that graph. Continuous time quantum walk converted to discrete time. And that's our algorithm.
Where did we see that the connection with the spectral gap and the time? The time is exactly 1 over the spectral gap, which is 1 over the
Yeah.
Witness size, exactly.
Yeah. I tried to give intuition for that. if the spectral gap is like epsilon, 1 over epsilon spreads it out, it's a standard thing. It's phase estimation. I didn't mention that, but.
And that's why you get the quadratic speed up over the obvious, I don't know, normal walk.
For certain cases like Grover search, yeah. So here are the main corollaries. We get this equivalence between quantum query models and span programs, and we get optimal quantum algorithms for total and partial functions. Sorry, the adversary bound is optimal in all these cases. I wanted to mention some classical corollaries. So first of all, it gives an upper bound on the approximate degree by the adversary bound. Secondly, one can get rid of this log factor for the sign degree of the polynomials. This is what Troy pointed out. So we know that the query complexity of the depth k function is at most the witness size to the k. It's also known that the adversary bound is supermultiplicative under composition. Combining these two theorems, you get the corollary that the query complexity of f to the k to the 1 over kth power is exactly the adversary bound without any log factors, just from that. And now if you plug in Lee's theorem that says that the sign degree is supermultiplicative under composition, that gives you exactly what you want. So the sign degree is less than the approximate degree, which is less than the adversary bound.
Sign degree is just the lowest degree of polynomial that agrees with the f in sign.
That sign represents,
No
yeah.
offense to Troy, but isn't it Cherstow? I mean,
Huh?
Cherstow result, he proves that the sign degree is multiplicative.
I don't know.
Okay, I wish maybe it's a different.
I don't know.
Maybe it's a different notion of multiplicativity. Yeah.
You're talking about something that is going to appear, that's still
It's going to appear.
so maybe so best
Well,
it's independent.
So has it appeared or is sign degree?
Well,
So mine.
Anyway,
Yours.
Oh yeah. Well, I just put on the archive the sequence.
okay. Yeah, so one corollary of this is that the sign degree for an and/or formula is at most squared of n because the adversary bound is. I wanted to say something more about the formula evaluation problem. Here's sort of a summary of what we knew classically versus what we know quantumly. So classically, we studied, of course, the OR function. It's trivial. It's n. In the balanced and/or case, and also some other cases, like it's called well-balanced, we have an understanding classically. In this case, if it's balanced binary, it's n to the 0.75. In general, we have this lower bound. For the majority function, we just have quite a gap between the lower and upper bounds. Quantumly, we understand these first two cases now. Of course, Grover search and the result by Farhi et al. In general,
can you remind us again why it follows trivially from your result, this upper bound of square root 10, or maybe up to this log factor?
Yeah. Shall I do that?
Yeah,
So, can people see this board?
we can put the light on.
Maybe. No, let me just do that because that.
Yeah, no,
Right. So. So let me start by saying this is a graph that corresponds to the span program for AND, right? If you've a plus one here, you need to be able to use both of these inputs to cancel it out at both of these vertices. So that's AND. And here's OR. If you have plus one here, you can cancel out either on this side or in this direction. Okay? And so now we look at composition. So composition of span programs, there's two ways of composing them. One that's really easy is just to plug them together. So if you take this graph here and you plug onto it an OR, that computes the AND of the OR. And if you have two ORs, it computes the AND of both ORs. Right? You can see because you want an and, you want to have both of these vertices, and the only way you can have support here is if you have the or. Okay? And so what Farhi et al. Looked at is they looked at this graph, and actually you can eliminate these edges here if you like, because there's just two of them, they cancel out. And so they looked at this graph actually. And so on.
It corresponds to a tree of nans or something.
It corresponds to a tree of nans, yeah, which is the same as ands and ors. And so now this will compute the NAND formula in the same way. You can have something supported here exactly when the NAND evaluates to true, when you have this condition that you add edges on the false inputs. And so I want to figure out what the witness size is, which is what is the squared support of this eigenvector. So we want a plus 1 here. So to cancel it out, I need to put a minus 1 on one of these two, whichever one evaluates to true. So I put a minus 1 there, and I also need to have an and, so I put a minus 1 here. And similarly, at the next level, I'll have to put a plus 1 on one of these two, and I'll have to put a plus 1 on, let's see, maybe there and here. And so the point is, at every 2 levels, I'm doubling the support of the eigenvector. And so if you look at if you compute the squared norm of this eigenvector, it's a geometric series dominated by the last term, which will be, let's see, every 2 levels is doubling, the number of levels is log, so 2 to the log over 2 equals square root of n.
And I mean, but you sort of assume now that you put the integral weights, you go plus 1 over.
So it gives an upper bound. It gives an upper bound.
This is the upper bound.
Yeah. So
Quite elegant, but don't you just get it by the multiplicativity of the sign norm?
yeah, but I didn't.
Of this plus minus adversary.
For the lower bound, you get it by the multiplicatively. For the upper bound, you need the multiplicativity of the witness size, which I didn't get to. I have slides, but it's simpler just to draw a picture here. Yeah, so the same argument that I'm drawing here, this goes through in general, not just for and or formulas. I'm just giving an example. So that tells us the witness size in the true case. In the false case, it's the same kind of argument. It's also going to be square root of n. So the witness size in both cases is square root of n. By that theorem, you get a spectral gap of 1 over square root of n, and everything goes through. So it's just this geometric series, and you get the algorithm essentially. So it's fairly simple. Yeah, and so let's see. Here, I just have a couple of slides on composing span programs, and so here's the first way of doing it, which is, say here's a span program for majority, and here's a span program for and here's their composition. So I've sort of taken the tensor product of this graph with this graph along this bit. So I've doubled these 2 bits and connected them according to this graph. And that will compute the composed span program. It's easy to see. It's also
Composed only in one coordinate.
in one coordinate here, in this first coordinate, these first 2 bits. And one can also see how the witness size transforms. I think it's a little bit easier to use what's called direct sum composition, which is what also was used over there. That's the kind of graph that Farhi et al. Studied. And so here, you just plug the target vector of one span program below the input vector of another, and you call that free. And so here, the only way we can reach this target vector is if we have at least 2 out of 3 of these columns. The only way we can use this column is if we can cancel out this last term, which is only possible if this majority evaluates to true. So that's how you compose them. And in terms of graphs, you can either put it like this, which is how I drew the biadjacency matrix before, or you can just spread it out so it looks nice. And this is what I mean when I say the structure of the quantum algorithm tracks the structure of the formula, right? So the quantum algorithm is a quantum walk on a graph that looks sort of like the formula. Here's a majority gate, and they're connected by an edge. And so here I plugged it in for the recursive majority formula. This is what the graph looks like. One can verify that the witness size is submultiplicative under both of these kinds of composition. And corollary is that the adversary bound is submultiplicative, so in fact it's exactly multiplicative. This wasn't known before. And this is an indirect proof. There's actually now a more direct proof. But substituting this all together, for an arbitrary formulas, we understand the query complexity perfectly up to the log factor. For time complexity, all these results are also good for time complexity up to log factors. In that case, the main problem there is how do we actually implement these quantum walks? So if you have a very dense graph, then it can be hard to implement a quantum walk. If you have a graph that has a large norm, that'll be hard to implement the quantum walk. And so to get these results, you need to be able to bound the norm of the graph and also the degree. Let me finish by saying what some open problems are. One is what happens for non-Boolean functions, and I think Troy understands this maybe, or Troy understands at least what happens for the adversary bound. So of course, if you have a non-Boolean function, you can encode that into binary, but it wasn't known that the adversary bound was stable under this encoding. Maybe it is now. First, it's not clear how you generalize span programs. There are ways of generalizing them for non-Boolean functions. But the dual of that SDP does not correspond to the adversary bound. It's not clear how the witness size composes for non-Boolean span programs. It would be interesting to draw some connection between the adversary bound and certificate complexities. Possibly this can be done using span programs. So for span programs over F2, you can draw a connection between some analog of witness size and certificate complexity. In general, it's not clear. So really, we know that the regular adversary bound is upper bounded by the product of the certificate complexities. One nice conjecture might be that the general adversary bound is lower bounded by that same product. I don't know if you could show that. Another question is what happens in this conversion from continuous to discrete time? Is that log overhead necessary? Maybe a classical question is, can we evaluate span programs classically efficiently? If you could, then you get a relationship between classical and quantum query complexities. And you don't expect this for arbitrary functions. You expect it only for total functions. So maybe this is a long shot. Really, what we care about is time complexity, not query complexity. And this is more poorly understood. We do know the following sequence of reductions. So I can take a quantum algorithm with one-sided error that has time t, and I can convert that into a span program that has witness size order t. Actually, it's what I call the full witness size, which is slightly different. And from that span program, we can apply our conversion. We can apply our algorithm, and we get a quantum algorithm that has time actually t, without log factors in this case. But the problem is I've gone from a one-sided error algorithm to a two-sided error algorithm. And so there's not an equivalence here. It's not clear what the relationship between between span programs and time complexity is. And finally, the most interesting problem is to try to apply this framework to try to come up with algorithms for more problems other than evaluating formulas. I mean, the reason span programs work so well for formulas is that they compose so easily. You can just plug them into each other, like over there. It's not clear whether they'll be helpful for other problems. They don't have any real structure, which means that it's hard to come up with intuition. I mean, all our intuition for coming up with algorithms uses these things that we don't have. You use workspace. You use I don't know, recursion or all sorts of things. And span programs, it's just an algebraic thing, and we don't really understand how they work. So that's not to say that they won't be useful for finding more quantum algorithms. It's worth investigating to try to figure out if we can develop some intuition here. That's it. Thank you.